Hey, welcome to day 2 of the review for physics midterm. Yeah, I'll add some clause in later. I'll edit it in. That's fine. Okay, it's still early. All right. So the learning objectives that we're covering today. Well, before we talk about those learning objectives, I want you to consider this essential question and try to extrapolate what the question is. The part of it that's off the screen. That's part of science. Extrapolating from incomplete data. In fact, there's only 2 types of people in the world. Those that can extrapolate from incomplete data. So the essential question is, how does Newton's second law of motion relate to the learning objectives of accelerated motion? I'll add in some laughter for that too. Okay, I got some laughter. So at least they're smiling. Okay, it's not funny enough to laugh. All right. So think about this essential question as we go through the learning objectives of accelerated motion. How is Newton's second law, which is really about dynamics and forces, related to sort of the kinematics ideas of accelerated motion? So we can kind of connect dynamics to kinematics. Kinematics being the study of motion without regard for what's causing that motion, and dynamics is sort of like, now we care about what's causing the motion, forces. So Newton's second law of motion is force is the rate of change of momentum. And if mass is constant, we can think about force being proportional to the acceleration. And so the quantities force, mass, and acceleration are related by the equation F equals ma. You can kind of see that if mass is constant, we can factor it out. This mv being the final momentum and mu being the initial momentum. So factor out mass, v minus u over t is acceleration. Because we have defined acceleration here as the rate of change of velocity. All right, so the rate of change of velocity is the vector quantity acceleration. So that was the first learning objective belonging to accelerated motion. Let's just define it. Okay, define acceleration, the rate of change of velocity. So change in velocity divided by change in time. So if we plot velocity against time, we have a velocity time graph. Because acceleration is the rate of change of velocity, it's the slope of this, right? So the change in velocity is the rise, right? The difference in the y values is the change in velocity. And the run is the difference in the time. So if we start at the origin, time 0, here we have an object that's increased its velocity from speed u to speed v over time t. And the 2 key interpretive ideas with the velocity time graph are what we just mentioned, that the slope gives acceleration. And the other one is that the area underneath the curve gives displacement. As we were just talking a moment ago, before I remembered to start recording, we said that the units are a big clue to help you with any sort of a graph. If you know what the units are, you can think about, well, there's really only 2 things I can do: derivatives and integrals, slopes and areas. Okay, and so the slope of the graph is going to be these units divided by these units, right? And so the rise in meters per second divided by the run in seconds gives us the units meters per second squared, which are indeed the units of acceleration. Area is like a length times width, and so we take meters per second and multiply it by these units seconds, and we get meters, which are indeed the units of displacement. So the area underneath that curve gives displacement. And now we're back to considering the third of 5 learning objectives that we're going to review today: derive and use the equations of uniformly accelerated motion. All right, so I want to start once again with the graph of velocity against time measured in seconds, velocity in meters per second. We'll reach a final speed we'll call v, starting at an initial velocity u. This is 0, this is 0. And so the object is going to increase its velocity uniformly, right? So we're deriving an equation of uniformly accelerated motion. So it's going to be a straight line. All right, we've increased our speed uniformly from u to v over time t. Okay. I'm actually going to call this value right here t, time t. and you know, it's still, we're measuring time in seconds, right? So I'm labeling the axis sort of here, but that's actually the time t that we've taken to go from speed u to speed v. All right, let's go ahead and derive these equations of motion. The first one comes from the definition of acceleration. So we said that acceleration is the rate of change of velocity. So the change in velocity divided by the change in time. And once again, because the initial velocity is happening at time 0, the denominator is like t minus 0 or just t. To get the first equation of motion, we don't like fractions and we don't like negative signs. And so multiply both sides of this by t, and we get at equal to v minus u. And that's something sort of useful to keep in mind for later, that the product at is equal to the difference v minus u. And remember, v minus u is sort of this space here, right? So that's equal to at. V minus u is equal to at. And then add u to both sides, and you would get equation 1, v, final velocity, equals initial velocity, plus the acceleration times the time. So this is equation 1. It tells us that if we're going at an initial speed and we're accelerating, multiply the rate of change of your velocity, how much you're sort of picking up or decreasing your velocity, times the time that you're accelerating for. And then this will give you sort of like the added velocity that you add into your initial velocity to give you your final one. So the product at, it is a velocity, right? When we multiply meters per second squared by seconds, we get meters per second. It's like we're adding meters per second of initial plus the meters per second of velocity we picked up, and that gives us, our final. So it's sort of along the way here, we're adding this at. At each sort of unit time, we're adding a little bit more velocity to our initial. All right, the next one is going to come from the second idea. So this came from the slope, right? The slope gave us this equation, it's just the definition of area. Now we're going to, the definition of acceleration. Now we're going to look at the area underneath this graph to give us displacement. All right. Sometimes very clear, like it'll edit it, and you can kind of see like, oh, the camera just focused. You can see it for a moment, and then it kind of refocuses. All right, so that looks a little bit better from my perspective. All right, so this is our line of our uniformly increased velocity. So the area underneath this, I'm going to kind of break down into two different areas here, right? So I've got the area of this rectangle, and I've got the area of this triangle. The area gives displacement. So let's sum both of these areas. Displacement, we use the letter S for that in this course. And so the displacement that is covered because we're moving at initial speed u. Like if we never accelerated and we just kept moving at this speed, we would just have, well, distance equals velocity times time, right? So just like if I need to go 200 miles south to Miami, I just go 200 miles an hour for 1 hour, right? And then I'm there. Or maybe not, maybe we'll make it there. Because that well exceeds the speed limit, but you get the idea. A constant velocity times the time gives you the distance. 200 miles an hour times 1 hour, here in Miami. But how about this piece? If we are accelerating, we're going to cover some more ground. Okay, we're going to cover even more displacement than if we just stayed at that constant velocity. And so we need to add in this ut, right? The initial velocity times time, so just length times width, right? The area of this rectangle. Now we need the area of a triangle. And so the area of a triangle is 1/2 base. And so the base of this triangle is here. And remember what I said, it's equal to at. Okay, so this base is at, right? Because it's the same thing as v minus u. So 1/2 base, the base is at, times the height, which is still t, right? The same as like the width or the height of this rectangle. So 1/2 at times another t is at squared. And so the total displacement is just going to be the sum of these two terms, right? So I'll have an equation of motion that says the displacement, how much, the net change in position of something that's accelerating is going to be equal to the initial velocity times the time plus 1/2 the acceleration times the time squared. All right, so this is a way to calculate the displacement if there's an initial velocity, the acceleration, sort of know the time to calculate that. The other equation that sort of solves for displacement is by averaging these velocities, right? So if we're going from speed u to speed v, we can sort of think about this average velocity that we've got sort of in between them. So this would be like v plus u over 2, right? If I average those velocities, sum them and divide by 2. So this velocity here isn't u, it isn't v, it's the average of u and v, right? v plus u over 2, or u plus v over 2. All right, so now we're going to take the area like underneath that, okay? So we sort of created this, we said, yeah, we're starting here, we're ending here, but on average, we're just going this way, okay? So we're sort of averaging the velocities and saying, let's take the area underneath that. So that's just a rectangle, okay? So it still is a area problem. We're still solving for displacement, but now we're considering the area underneath. What do you think? Hypotheses? Oh, okay. All right, so to make it a little bit more clear. Okay, structure this time squared. We've got the good equation over here, right? So now we're taking the area underneath this sort of red line, if you can see that, and that's representing the average velocity. So it's length times width. The length, we'll call it sort of this way. So it's v plus u over 2. What's another way to write that? 1/2 u plus v, right? Same thing as u plus v over 2, right? Same thing. So length times width. The width is t, and there's my third equation of motion. So I've got an equation that relates final velocity, initial velocity, acceleration, and time, no displacement. I've got an equation that relates displacement, initial velocity, time, and acceleration, no final velocity. I've got an equation that relates displacement, initial velocity, final velocity, and time, and no acceleration. Because remember, we just sort of said, forget the acceleration, we're just average the velocity. Just say we're moving at this constant velocity, right? That was sort of the approach for that one. And then finally, we're going to derive an equation that does not include time. You see how time is in each one of these. And so what we need to do is kind of think about how can I eliminate time, all right? I want to substitute in for time into this equation. And so let's go back to this original definition of acceleration and solve it for time. And so in terms of these variables, what is time equal to? Multiply both sides by t, divide both sides by a, or do the old algebra switcheroo there, and you can find that t is equal to v minus u over a. So now we will substitute in v minus u over a for t and see what equation we get for that. So we have s equal to, I'm going to rewrite this sort of back to this way again, u plus v over 2 times t, and remember t is v minus u over a. All right, how do we solve this now, or how do we kind of combine this? We've got fractions, all right, so we go numerator times numerator gives me my new numerator, denominator times denominator gives me my new denominator. I'll just do the denominator first, there, 2 times a. Now I'll let you all do the numerator there. Save the easy stuff for you all. We'll go through it together. What's u times v? uv. What's u times negative u? Negative u squared. Right, I'm just distributing this u. Now distribute the v. V times v, positive v squared, and v times negative u is negative uv. So uv minus uv is 0, and I'm left with s equal to v squared plus u squared over 2a, or I'll say u squared plus v squared over 2a. And remember, we don't like a fraction, so if I multiply both sides by 2a, I can get 2as equal to u squared plus v squared. And we typically write this equation with v squared as the subject. Oh, this is negative v squared, okay? We want v squared to be all by itself, and again, we don't want the negative sign. I dropped the negative. Remember, u times negative u is negative u squared. Take care to not drop that negative. All right, so you get the correct equation. So if I add u squared to both sides, remember, we don't like a negative, then I'm going to get my final equation. V squared equals u squared plus 2as. And again, you just add u squared to both sides. So it's u squared plus 2as. On that side, u squared all by itself. And so this is one that we typically call equation 4. So we have equation 1, v equals u plus at. Equation 2, s equals ut plus 1/2 at squared. Equation 3, s equals 1/2 u plus vt. And then equation 4, v squared equals u squared plus 2as. That's just this part of it. Deriving the equations of uniformly accelerated motion. Once you've got them derived, now we can sort of use them. And so we'll put these equations to good use with, solving different problems. So anytime you can recognize there is uniformly accelerated motion, these 5 variables, displacement, time, initial velocity, final velocity, and acceleration, those 5 variables are related with these 4 equations. Any given equation, omits one of the variables, right? It's like this one doesn't have time because we substituted for time. And as I mentioned earlier, each one of the other equations, is missing one of the 5. In order to solve for anything, you have to know 3 of them, right? So each equation relates 4 of these 5 variables, right? Because each equation omits one of them. And so in order to solve an equation with 4 variables, you have to know 3 of them, right, to solve for the unknown. And so keep that in mind as you go to approach these questions. You're thinking, what do I know here? It's not always given. It's sometimes the question expects you to know something as a student of physics. For example, the acceleration due to gravity. The question isn't always friendly enough to say, remember, you're on Earth with a gravity field strength of 9.81 meters per second squared, accelerating things that fall. So like we do a free fall lab, right? Describe a method. So that's the derivation, and then we'll do more practice problems with using those equations. Like questions that might involve the acceleration due to gravity. The learning objective was describe a method for determining the acceleration due to gravity G. And you may recall that we kind of looked at sort of 2 different labs to do this. One was called the drop lab. And this is where we kind of think about the equation S equals ut plus 1/2 at squared. And we consider dropping something a displacement S. Okay, so if we're dropping it and it's vertical, we typically call the vertical displacement H for the height. Okay, we're sort of dropping the height. And if we just drop it, the initial velocity is 0, right? We're not like throwing it down and throw it upwards into the air. And so the initial velocity is 0. And so we sort of think about this as the displacement is H. There is no initial velocity, and so that term sort of just goes away, it goes to 0. And then we have 1/2 the acceleration due to gravity, call it G, times time squared. And so we thought about a lab method for determining G by dropping things a given height and timing them, and then plotting a graph of the height against the time squared. So if we plot the height in meters against the time squared in seconds squared, then the slope of the best fit line for these data points, right, if we sort of vary the height and then measure the time squared, or measure the time and then squared and then plot that, we get sort of this trend that it takes things more time squared, to fall from a greater height. right? The higher up it is, the more time it takes to fall. So that's kind of intuitive. And this tells us how those sort of quantities relate. How does h sort of vary to give us t squared, or how does t squared vary to give us h? 1/2 g is the slope of this line, right? Because we have sort of an equation of a line, y equals mx. And so by plotting h on the y-axis against t squared on the x-axis, we can see that the slope of our best fit line should be equal to 1/2 g. And so by plotting our data, finding two good points on our best fit line with coordinates, t squared 1, h1, t squared 2, h2, right? Or y2, x2, y2, x1, y1, right? Use the slope formula. We'll know what the slope is. Right? We'll have a numerical value for that. And then the analysis is just to set that slope, right? That number for slope that we get by doing our slope calculation equal to 1/2 g. And then g is the only unknown. We can solve for g. That is a laboratory method for determining g, right? So dropping something and timing it. And so take a look in the link right there if you want to see the drop lab data collection. The other way that we did it was with a pendulum, right? We let a pendulum sort of oscillate in Earth's gravity field, and theory suggests that the period of oscillation is also related to g and the length of the pendulum string. So we sort of varied the length of the pendulum string and did a very sort of similar experiment. We're just sort of timing the oscillation. So you can check back into your notes sort of about that. All right, and we're going to try to sort of connect a lot of these ideas here as we go through the last of these learning objectives. The whole chalkboard for that. That could happen. All right, so we have explain projectile motion in terms of horizontal and vertical components of motion. I've got a figure over here, which has a initial velocity vector v, directed at some angle theta above the horizontal. We could resolve this vector to determine the horizontal component, dx cosine theta times v, and the initial vertical component of velocity. It's initial because gravity accelerates, okay? And that would be sine theta times v. The key idea with explaining projectile motion in terms of horizontal and vertical components of motion is that the horizontal component of motion is non-accelerated motion. That's what we reviewed yesterday, right? Non-accelerated motion in the horizontal direction. Gravity does not accelerate things in the horizontal direction, but it does accelerate things in the vertical component. So we have non-accelerated motion in the x direction, in the horizontal direction, and accelerated motion in the vertical direction. Gravity is the accelerator. Just the force due to gravity, right? Accelerates. So the acceleration due to gravity is what we are determining with that lab work, local g. And we know from our experiments and from the literature that here on Earth, gravity accelerates things in this direction, always, right? Gravity always acts straight down, and g is, so if we think about, down is negative, like if we launch something up and we call that direction positive, then it's a vector, right? The acceleration is a vector as we define. So you kind of think about g as being negative 9.81 meters per second squared. So that's like the acceleration due to gravity vector. That's constant, right? A constant acceleration due to gravity. And so we can use those equations of uniformly accelerated motion because gravity is sort of a uniform accelerator. So what I've got here is a little sample problem. Well, I've got a sample idea up here. We're going to turn it into a problem that may culminate before the end of all of this with a field trip out into the courtyard. And so let's consider what we've got to do in order to do that. The question that I pose is, could I launch something off of the 37 balcony? It'll reach some maximum height and fall, but not land at the same elevation that I've launched it at, which would be sort of equal to about the guardrail there, but rather allow it to continue to fall until it hits the ground about, I don't know, this roof is 3 meters, and so that might be 4 or 5 meters, we might say, 4 or 5 meters sort of to get down here. And so how could we calculate the time it would take? And so let's sort of think about what equation of motion is going to be helpful here. Let's calculate how much time it would take the object to travel and hit the ground, okay? All right. We're going to start with an equation of motion. S equals ut plus 1/2 at squared. The displacement is going to be the difference from where I throw it to where it lands, okay? It's going to travel, upwards, but then it's going to fall and it's going to be 0, right? Like this is only the y direction, right? Remember, we only apply these equations of acceleration in the vertical direction. That's the key idea with this learning objective. Accelerated motion in the vertical, non-accelerated motion in the horizontal, which is why, remember, the horizontal distance range is just vxt, no acceleration, right? It's this part of the equation with no acceleration. Range, that's the x direction, equals vxt, okay? But in the y direction, we've got to consider gravity's acceleration. So let's say that change in position is, let's say 5 meters, okay? From the 37 sort of guardrail to the ground, and we'll call that -5 meters, okay? Because we're going to make down negative, all right? We're going to be consistent with this. So we've got to be consistent in our sort of sign convention. So the displacement is going to be -5 meters. I'm not going to drop it, okay? I'm going to throw it up in the air, or one of you, may have a chance to do this. And so how fast can we throw, all right? Or what's a reasonable estimate? Is there a way that I could experimentally determine how fast I can throw up? So that's like, this is a lab that we do sometimes. How fast can we throw up? It's like, what? It's like throw up into the air, like the vertical component of motion. We calculate the speed of our throw up, our up throw. How can we do that? Well, if we think about our h equals 1/2 gt squared, if I throw something up in the air, I could time it. That would tell me how high up it goes. One of these equations got to be helpful over here. Let's kind of think about it. If I throw something up in the air with an initial velocity, it'll eventually reach a speed of 0 unless I throw it really fast, right? And get it like into orbit or something, or it leaves Earth's gravity field. So gravity will eventually slow it down to 0. So I want to know my initial speed u. I know it's going to reach a speed of 0 after the -9.81 meters per second squared of gravity acts on it for a certain amount of time, which I could measure, right? So I could just time how long it takes the ball to get up to maximum height, or I could let it, time it all the way down and divide it by 2, right? That idea of symmetry of motion. So I think equation 1 is enough to let me do a quick little experiment. How fast can I throw something up in the air? So we're gonna do that right here as a precursor lab inside the laboratory, so that I've got a more reasonable estimate for you here, the speed of my up throw. All right, so students in class can watch out. Now I'm going to catch the projectile because we don't want to time it all the way to the ground. because then it's, you know, more time than, so it's sort of like from equal elevation, right, up and down. So how fast am I throwing? So we're going to time from release to catch. Half of that time will be the time we need for V equals U minus 9.81 t. So half of the time measured will go here. We know that it will reach a speed of 0. So we're really saying, like, however fast I throw it, that time times 9.81, that's the negative of it, right? Like I throw at a certain speed, and then gravity times the 1/2 time is the negative of this value to make it 0, right? Like whatever this is, that's the absolute value, right? The positive of it. All right, so timer's ready, e-learner's ready. You want to record your own data here. I'll do a 3, 2, 1, okay? 3, 2, 1. What time data do we get? 0.99. We'll just round it up to 1, and we'll say that it reached maximum height at 0.5. Did anybody get any time data themselves? 1.09, 0.99. Did you time it? 0.96. That's all pretty consistent. Okay, so we can feel good about a second, you know, half a second. Probably that's like, it's kind of like human reaction times and stopwatches, but you know, okay. So we have 0.5 seconds t minus negative 9.81 meters per second squared. Um, 9.81 meters per second squared. So you see that the units of this really are a velocity. All right, so meters per second squared times seconds is just meters per second. So I'm subtracting away these meters per second from my initial velocity to get 0. So it's like adding this term to both sides to solve for u, just think about more algebraically. And everybody with a calculator knows that 0.5 times 9.81 is 4.905, right? You know what's confusing about that is that we just happen to have a 1/2 in our equation, you know, and happen to be half a second. All right, so 9.81 times 0.5, 4.905. And so I threw that with an initial velocity of 4.905. So we'll say, you know, that is going to be kind of confusing because half of g is also 4.905, right? And we like that happens to be what this is. So I'm going to throw it a little bit faster. Okay, I'm try to get as close to the ceiling as possible. I want to try to make this just a different number because I want them to be distinct. I was like, well, what is 4.905? Like every time we take 1/2 g, we're going to get that constant 4.905, and like that's kind of embedded within this. And just by coincidence, I happen to throw it like to give us the same, you know, coefficient here. But there's nothing wrong with that. Like we can still solve it, but I'd rather have these numbers be different as we do the rest of the time. So I'm gonna throw a little bit faster. Let's time that again, okay? Get that half a second out of there. All right. So here we go. Redo. It can't hit the ceiling. That's a force. We're relying on just gravity alone being the force here. That's sort of an assumption. Redo. Ready? 3, 2, 1. What'd you get? Exact same? No, what'd you get? Okay, we'll say 1.06 is the mode of the, a little, you know, math review, the mode. We'll go with the mode here. What's half of 1.06? 0.53. That'll make it a little bit different, right? Not too much, but. So now we have 9.81 times 0.53, 5.2 we'll call it, okay? So I threw up with a speed of 5.2 meters per second, okay? My initial velocity in the y direction. So let's keep that in mind, that we're gonna let the ball fall 5 meters. I'm gonna throw it upwards, so I'm gonna throw it with positive 5.2. I'm going to go ahead and drop the units for the equation. Just keep in mind, everything's going to be in SI. So meters of displacement, meters per second of velocity, seconds of time, meters per second squared of acceleration. All right. And so that way we can just kind of look at the numbers. It's less cluttered. And then when we solve for time, that's what we're going to solve for. I want to know how much time is it going to take it to fall. We'll put the seconds back in. So positive 5.2 t. Now minus, right? Negative 9.81. So we got to subtract here. Remember what 1/2 of 9.81 is. Okay, I'm going to show sort of 1/2 9.81 t squared. We could evaluate this. What's 1/2 of 9.81? 4.905. You may recall a moment ago I said, oh, I wanted to change my speed a little bit faster because I didn't want those numbers to be exactly the same. It's like, where did this come from? Oh yeah, it's my initial velocity. And if they're the same, it's kind of not as easy to see that. 5.2 t. Don't need to really write the positive sign, but I do need to remind myself that that's negative. Okay, so now we're going to solve for t. You all ready? Here we go. I'm going to rewrite these terms on the left side of the equation. It's going to look like this. Negative 4.905 t squared. This is positive, plus 5.2 t. I'm going to add 5 to both sides. Right? So like I want all of my terms together on one side of the equation. So this is negative 5 over here. So it's plus 5 if it's over sort of on this side, right? If I just added 5, you can see it's positive 5 over here, and it all equals 0. Does everybody see what we've got? You learn some because it's like blocking. Okay. Does anybody recognize that? Does anybody know how to solve it for t? How do we solve this for t? You should recognize this. A standard form of a quadratic equation, okay, where negative 4.905 is the coefficient A, positive 5.2 is the coefficient B, positive 5 is the constant term C, and we've all set it equal to 0. And hopefully you know how to solve for x if you have a quadratic equation in standard form. It's a quadratic formula. This is the answer to the question. When are we ever going to use this? You're going to use it in physics class right now. We're going to use the quadratic equation to actually solve for a real world problem. How much time is it going to take this tennis ball to hit the ground? Okay, with realistic values. Okay, we're really going to let it fall 5 meters. I'm really going to throw it just as fast as I did a moment ago. We're going to go out to the 37 balcony and do this, and we're going to time it and see does our calculation match. But first, okay. You've probably learned it as x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. So we just got to keep track of all of that. We're solving for t, not x. So it's the same thing, right? T is the variable. So x equals t equals negative b, so negative 5.2, plus or minus the square root of b squared, 5.2 squared, minus 4. A is negative 4.905. C is 5. All over 2 times negative 4.905. All right, so we got that. Let's solve underneath the radical first. I get 5.2 squared minus 4 times 4.905 negative times 5. So I get underneath the radical 125.14. So I get negative 5.2 plus or minus square root 125.14. Is anybody else not far along? And then twice this just brings us back to 9.81. So we divided this by a half to get that. Anybody else corroborate this underneath the radical? Good. And then let's take the square root of it. 11.18, 11.2. So I have negative 5.2 plus or minus 11.2, we'll say, over 9.81. So I have one solution, which is going to be negative 5.2 plus 11.2. So 11 point, let me just clear this up. So 11.2 plus negative 5.2, that's 6 divided by 9.81. So I get one solution that says T should be equal to 0.61 seconds, okay? But I get another solution that says negative 5.2 minus 11.2. That's negative 16.4 divided by 9.81. And I get one solution that suggests that the time might be negative 1.7 seconds. So what does your sort of instinct tell you about this? What's a more apt hypothesis based on our calculation here? I got two answers. But what do you think? Will the tennis ball hit the ground after 0.61 seconds or after negative 1.7 seconds? Yeah, like it's not going to probably like go back in time when we go out there. That'd be cool. It's like, wow, we got the negative answer. I think like mathematically, we're solving for like maybe like the other side of the parabola over here. Because it's like the intercept, right? Like we plotted this on the time axis, like you're calculating like a parabola crosses the t-axis, the x-axis in two places. But like if time is this way, we kind of have to move forward in time. So like we really are solving for like, we could travel back in time and be negative 1.7 seconds. You know, that's what it would cross, it's negative t. You know, and that's kind of the interesting thing about math is that it's abstract, and you kind of say, well, you can't really do that, and so we can kind of discard this solution, but still kind of consider it like kind of interesting and say, well, this is a positive solution, like we're moving forward in time. So 0.61 seconds. There you go. Now, the way to avoid this, so you never have to do this again, is just calculate from here how much time it would take this thing to fall, okay? Because as soon as it's at maximum height, this term goes to 0, and then you just have our h equals 1/2 gt squared, the same equation that we talked about for the draw plot, right? And then you can just solve for the time by taking the square root of both sides, right? You don't have this. The reason this is tough is because the t is connected to both of these terms, right? So you have to use a quadratic to solve it. But if we could somehow get this term to 0 by saying, well, I'll just break it into 2 steps. I'll solve for the time from here to here using equation 1, because I know like the same way that we sort of got my velocity, right? We could say, well, we know the final velocity is 0. You know, I could figure out the time to get to here, all right, if I know my initial velocity. And then you can calculate how much time it would take the object to just fall all the way to the ground from there. So you have to kind of also know the added height, right? Because this is the net change in displacement. Sorry, the other sort of neat thing about these equations is that you're sort of, you can plug in any value for t and get the displacement sort of along this here. Like when does this thing reach maximum height? What would the displacement be? So like if we plugged in the time that it would take it to get to maximum height, then this answer should be, you know, positive because it's going to give us like our displacement sort of above there. So having an equation, you know, allows you to sort of solve for any sort of step along the way, right? So like we plug in any value for time that we want to. All right, so I think we're good now to go and test this idea. We're going to time how long it takes to hit the ground. Now, we didn't account for how far over I'm throwing it, okay? But does that matter? It only matters if I throw it really, really fast, okay? If you throw it so fast that like it starts to fall with the curvature of the Earth, then it will go into orbit, all right? And that would be like 8,000 meters per second. So I'm not going to throw it that fast. So we would hit something, you know, through 8,000 meters per second, not high enough up for it to sort of continue moving. So that's a sort of a famous idea that comes from Newton's Principia. All right, and so a few years ago, a student painted this. This is the only illustration that Newton included in his famous Principia Mathematica, where he kind of said, yeah, if you had a cannon with enough gunpowder on a tall enough mountain, you could launch it and it would fall around the Earth, right? Because as gravity sort of brings it down, the Earth sort of curves away from it. And so if it was fast enough, because the curvature of the Earth is like every 8,000 meters you go over, it drops down 5 meters. And that's the amount of distance that something will fall in 1 second. Okay. All right, so e-learners will bring you along for the travels here. How much time we got left? It's 9:38. We dismiss at what, 10:07, and so plenty of time when you go out for a quick bit of data collection. If you want to, if you prefer to just like stay here in the lab, that's fine too. You could just use the time the way that you see fit. We'll just prop it. All right, come on, e-learners, we're going. We're gonna let the e-learners actually throw it, so like from this perspective. The e-learners will throw it. All right, and so let's go along this sort of corridor right here, and I'll go up to that part of the 37 balcony. All right, so we're gonna sort of be along right here. You all have stopwatches. E-learners. Testing the PSAT. So remember, they're testing the PSATs. In what do you think, learners? Is this like, you have to save this for another lab day, or? Just be quiet. We'll just be quiet. All right, we're going. Oh, one little. Stop it. What time data did we get? Yeah, something seemed too low about this answer. Because you just drop something from 5 meters up. How long does that take to hit the ground? So if we just did h equals 1/2 gt squared, so h is 5 meters. We just did 5 equals 1/2 gt squared. Divided by 4. Yeah, that should just take a second to fall. So if we throw it up in the air, but we made a mistake somewhere here, which I did intentionally, so that we would have a chance to analyze it afterward to check the sort of reasonableness of this. It's also possible that I didn't throw it as fast, okay, as there, but still the problem remains. If you just drop something, right, from the top of that, it should take about a second to fall. So where did we go wrong here? A mystery for another day. Okay, maybe this. All right, anyway, it doesn't take away from this idea, which is explain projectile motion in terms of horizontal and vertical components of motion. Well, I'll kind of think through this one here. That's sort of part of the fun of science, is that, you know, you get to kind of learn from your mistakes. Hopefully you can recognize, you know, when you sort of, there's an obvious error. So it bothers me that we get 0.61 seconds here, when if we dropped it, we can calculate that it should really be 1 second. So I kind of was suspicious about that when we first calculated, like, yeah, it seems a little bit too low. So I'm like, well, we'll just go out and do sort of what scientists do and test it. And I was kind of suspecting that the data would not corroborate this answer. So where did our thinking sort of break down here? Maybe this negative part. Anyway, a couple minutes left in class. We'll sort of call it a day there and tune back in tomorrow for the conclusion of that, where we try to get to the answer. E-learners, you're dismissed. Everybody else, we got a couple